Welcome to Coding Adventures. In today's episode, we're gonna try to implement an emulator for this famous computer of the 1975 and 1970s called Altair 8080. 8080. So this computer was first published in Popular Electronics magazine in January 1975, and since then it started an entire revolution in the microcomputers, as you know. And today we're gonna try to implement in JavaScript an emulator for this computer, and eventually even we'll run basic interpreter on top of this emulator. So let's get started. All right, so before we actually start the actual coding, let's start with a little bit of a history lesson around this Altair 8800 computer and what it meant for the times and what it means for the current times. As I had mentioned, it was first, the Popular Electronics magazine first published an article in January 1975 about this computer. And this article actually got attention from no other than Bill Gates and its co-partner Paul Allen, and they just contacted the company that built this computer and proposed them to build a basic interpreter for this computer. So let's go a little bit over some of this very historical data and understand a little bit more about the context and what they did actually back then. So this computer, as you can see in here, it was built based on the designs of the computers of the era, based on the mini computers. It has this panel with lots and lots of LEDs and lights. And what was different then in this computer was one of the very first computers built around a microprocessor. And actually that microprocessor was no other than the Intel 8080. And perhaps that's why the Altair is called Altair 8800 from the CPU. And even Intel, this is an original ad from that time, from 1974 actually. They are showing a computer built around this one. And actually this is a similar computer. And Intel 8080 was actually one of the very first microprocessors as well. Until then, microprocessors were not integrated on a single chip, but were kind of spread on a big PCB board inside the computers. And if we're looking here, the computer, as I mentioned, is nothing else but a box with electronics inside and LEDs on the front panel. It was popular back then in the days, especially for the mini computers, to have this kind of operating panel, and also mainframe computers of the day to be operated from all sorts of toggle switches and to see the status directly here. So what's inside this computer? As we said, it's an Intel 8080 CPU, which was basically an 8-bit CPU. One of the very first 8-bit CPUs, which inspired later on the Intel 8086 and then the entire x86 family of CPUs that we have nowadays in our modern computers. All right, so people at that day, they just assembled this computer from either by themselves or they purchased it from MIT. This is an article in the magazine, actually. I think it's on the page 33. Let me just try to reach that page really quick and see what they said about that computer back then. Still a few pages to go. All right, so well, they said it can be built for under $400, which was a great price even for the day. And this computer, it was just produced just like this. And in order to use it, people usually toggle these switches on the front panel, and and they then made various games with the LEDs to to kind of blink them, which was kind of fun for that time. But to use it a little bit better and to exploit a little bit more this kind of computer, the best was to attach basically what was called a terminal device. And this is actually a pretty popular one. It's a Teletype. I think it's Teletype model 33. You can see here, basically, this is similar to the input and output device of a modern computer. The difference is that instead of a display here, this is paper. So I'm just writing it on this roll of paper. So this is a roll of paper, and as you type on the keyboard, actually there is a serial connection between the terminal, and the Teletype machine, and the computer, and keys are sent one at a time via this serial connection, and whenever the computer wants to print something, we'll send it back again via serial connection and will be printed on the paper. You can imagine you waste a lot of paper doing in this way. You don't have a screen, but later on, when electronic terminals appeared, they could have been attached to this kind of computer as well. But this is kind of an original configuration, how people use it back in the day, the computer with a Teletype machine if they have one. And this is actually a pretty powerful configuration, because on this Teletype machine, you also have the ability here to load programs, not only to type them, but also to load them from rolls of punched paper. And it's like simulating a really, really quick typing here. And this is actually what these two well-known gentlemen did, Bill Gates and Paul Allen. They built a basic interpreter for this machine. They felt that this machine cannot reach its entire potential if it's not programmed in a higher level language. So they built this basic interpreter, and they reach an agreement and licensing to MITS, MITS being the manufacturer of this machine, and they ask various prices for the copy of that basic. And how was this basically, the story goes that basically they build it even without having a machine like this. They just implemented an emulator of the CPU, something similar to what we're gonna do today. The story goes that they implemented a simulator for the CPU, for the new Intel 8080 CPU on a mini computer, on a DEC 10 mini computer if I'm not mistaken, and they built the software on top of that, and the software just ran perfectly. For the first time when they went and they saw the machine, they just loaded the software, and the software ran perfectly. And as I mentioned, the software was nothing else but a roll of paper containing a basic interpreter. This is not the original one. This seems to be the 8K version. The original one was much smaller. But even this one, the more advanced one, it means that it takes it requires 8 kilobytes of memory. Still, you know, pretty low specs by today's standards. All right, so that was pretty interesting, and this basic was very, very popular back in the day. And what happened is that a lot of people tried to clone it or to copy it, which was basically not liked by Bill Gates. But before then, let me just show you, and I prepared here a series of links. I won't go to all of these ones, but I link some of this one in the comments so you can check by yourselves. Let me just show you here on this channel, basically, how this computer behaves in running. And this is not an original computer, actually. This is a clone. These guys are producing clones of this famous computer. You can purchase them, so if you're interested, you can go here and check out. But let me scroll to the video a little bit. And okay, you can see here basically the basic being loaded. Is loaded from the punched tape. It's similar to how you plug in a floppy disk or a CD or a memory stick in a computer and load it. But basically this was just paper full of holes. It took a while to load it. But once it's loaded, and let's it's an interesting video. Once it's loaded, you can see that the basic interpreter is starting up, and this Teletype machine, which is like a fancy printer connecting to the computer, will start to producing an output. It's asked for memory size. So it's a sign that the basic interpreter started correctly, and now basically the operator is supposed to type the memory here from the keyboard, and this computer apparently has 8 kilobytes. And as you can see, the computer starts to list, and you interact with it just typing it, and the computer prints back prints back the results. Now, of course, in our emulator for today, we're not gonna recreate the hardware, but we're gonna try to do something in JavaScript using a much easier and friendlier method to interact with this kind of computer. All right, so this is a very interesting video if you want to see it, just to see the computer in action. Here you can see typing a basic program, and this is a program written in this language called BASIC, and when it's run, the program will basically run on the computer and probably print some numbers. All right, so this BASIC produced by Microsoft was very popular in the day, which made people pirate it a lot, which prompted Bill Gates to write a famous letter. It's now the very famous An Open Letter to Hobbyists, written by Bill Gates in 1976, where basically he said that it's not fair for people to steal software and so on and so forth. It's a very interesting read, which basically it's also interesting from the historical point of view. Let's remember this was written February 3rd, 1976. Anyway, people back in the day, they didn't used to pay for the software. So you can also read about it on Wikipedia. People didn't like to pay for the software, which prompted a few more entrepreneur guys to write another basic language for this machine, which was basically Tiny Basic. Microsoft Basic was called Microsoft Basic, or 4K Basic, 8K Basic, something like that. Tiny Basic was an alternative Basic, which initially was published like a specification in a computer magazine back in the day, Dr. Dobbs, and then various people start submitting their implementation of this Basic, basically. And I have here one of these, the nicer implementation by Dr. Wang, and this one, I believe, yes, is from the 1976, was published in source code. So basically, as you can see here, in a few pages of the magazine, we can read it like that. Here you can see a small manual about how BASIC operates, about the syntax of BASIC language. And then the actual source code of this interpreter gets published in the magazine, and as you can see, the BASIC interpreter is written in assembly language for this Intel 8080 CPU. As a matter of fact, also Microsoft Basic was written in assembly language. Obviously, they didn't write it in another higher level language. They also wrote it in assembly, the same as with this Tiny Basic. And you can find all these historical magazines now online. You can study them if you want. But without further ado, I want to mention that in today's episode, what we want to create is basically a tiny clone of an Altair 8800 in JavaScript, and then we're gonna try to run on top of it this Tiny Basic. I don't have handy the original or the first Microsoft Basic for it, but you can still find it online. So if you find it, give it a try and you'll be able to run it as well. But what I found online is basically the Tiny Basic source code. Also the same one as the one printed in magazine. Actually, this one is on GitHub. You can find it yourself on GitHub. If you go GitHub Tiny Basic, let's see, not Tiny Basic, let's put 8080. I forgot exactly the place where I found it. Yeah, looks like this one. You can find the source code. But you don't have to assemble it and find tools to assemble this source code, because you can also find online this source code assembled. And as a matter of fact, I already have the source code assembled here, and which is basically nothing else but a bunch of numbers, exactly like the numbers from that we use with the virtual CPU from yesterday. And here, just a small parenthesis. If you are watching this video and you want to get a little bit of a background around how CPUs are working, check the previous video that the previous session from yesterday about emulating a CPU. So anyway, at our disposal we have this tiny basic. So actually let's start and copying it in a new source code. And yep, let's put it here for now and see how can we make this program, which we know for sure it's a basic interpreter written in machine language, how can we make it run on top of an emulated machine. Now, as we did yesterday, we need to emulate the machine. So let's grab a little bit the notebook and plan around this particular task. So inside that machine that we saw, it's basically nothing else. This is the machine. Inside it's a CPU. So it's Intel 8080 CPU. This is the CPU. Inside we also have a memory, and we need at least 4 kilobytes of RAM for this one. So let's say this is a 4 kilobytes memory. The CPU is connected to the memory, and this is inside the box, right? Inside the box there are also those LEDs and switches and toggles. We don't care about those ones. We just want to load somehow. This will load here inside the memory, the tiny basic. Basically that string of numbers, the 49, the 0, the 20, the 62, all these are going here. All these numbers are going inside the memory. Then we're gonna need to emulate the 8080 CPU, and we'll need also something else. Since once this program will start being executed, it will produce some output, and will also accept some input from the keyboard. And in the original Teletype, the one that I showed you, basically we had a printer here, a piece of paper that was printing with the output, and also we had a keyboard. It looks like a modern laptop, but I'm assuring you this was just a terminal device back then, connected to a serial. So here inside probably there is a serial interface, and somehow connected to a serial interface to the CPU inside. So this is basically the output, and this is basically provides the input. All right. Now, yesterday we implemented and we emulated a virtual CPU, a very small one. For this one, we're gonna cheat a little bit. We're gonna not write a full emulator from scratch for the Intel 8080, although it's probably possible, but will take probably a couple of hours, not a single coding session, but probably several. So instead of doing this, we're gonna find on internet somewhere, we need an emulator for 8080. So we need this piece of code. Then of course we need a tiny basic program. So these things we're gonna take them from somewhere else. Let's put them in different color. And then the rest we're gonna code it ourselves. All right. So what we're gonna code all this linkage between the CPU and the memory, between the CPU and the serial, and the interaction, and so on and so forth. So that will be basically will remain the easiest part. So let's find start and find a CPU emulator for the Intel 8080. And actually I was looking around and I found one on GitHub, which I think is very good for this task. Let me search for it. GitHub Intel 8080. There are several of them on GitHub. Also, many people writing this kind of emulators. I think I'm gonna pick this one. I hope it's the one that I saw before I studied. Actually, no, this one is in C. Let's see. All right, it's from Alexander. Okay, so I think he has two versions. I'm gonna pick the JavaScript version, which is basically on this repository. So let me just save this file for now. And because let me just save it. I'm just gonna save it on my desktop. .js.txt and name it txt for now. All right, is this file over here. And what I'm gonna do with this file, since I'm gonna use this environment, I'm gonna just copy and paste the entire emulator inside this code wrap environment. I'm gonna create a new page here. Let's name this one probably CPU. Yeah, let's name it CPU. And let's open the file that we downloaded from GitHub, copying entirely and paste it here. All right, a quick glimpse at the CPU emulator here. We can see probably it's implemented similar to how we implemented yesterday, that virtual CPU. It's a big switch, and each opcode is basically decoded, and various states inside the CPUs are set according to the opcode. All right, that's good. So we copied here the CPU emulator, and let me just save this one. And let me put a name. This one is basically Altair 8800 tiny basic. That's our intent to build. We put the CPU, and we have to go here back on the repository and read how we use this file actually. I think there is an example here. Let me look for it really quickly, if I can spot it. Maybe this one, test. Yeah, I think this is the one, the test that I look for it. As it appears, the CPU, I think it's also documented inside. Yeah, the CPU is implemented like a class, but the entire emulator is self-contained. We just have to provide two objects, one a memory object that has a certain specification and another one an IO object. This IO is a little bit new from what we saw yesterday. So in this example that it's provided here, we see an example. So memory, this is written in the legacy syntax for JavaScript, but we're gonna recreate it as a class. So we're gonna create a class memory that basically has three methods: read, write, and load file. All right, makes sense. So the CPU will probably invoke this read and write inside the memory in order to basically, read a byte, write a byte to the memory, and load file probably initially we're gonna use it just to load our basic interpreter inside here. And the other IO object, it has an input, output, and interrupt. All right, so let's document this one here on the paper, just to have them handy. So we have basically, we have the Intel 8080 class, and this one requires two properties. One being memory and one being IO. And now we have here memory. And memory requires, needs to have a read, a write, and a load file. And the write, the read will need to have an address. So basically read from address, write will have an address and a number to write, and load file is basically will have to load it there. All right, so actually I don't think we need a load here at all. We're gonna just load it ahead of start. So just a read and write, those are important. And then the IO, we're gonna need to have an input, and we're gonna need to have an output and an interrupt. All right, So memory, this guy goes to here, and IO goes to here. And for this one, we have the source code, so we have to implement the source code just for these two other classes, and we have a fully functional system. But before then, just a little bit of an explanation what this IO is. Memory is very clear what it is. Memory is basically this chip of data that contains memory cells where you can keep numbers inside, exactly like we did yesterday. So what is I/O? Well, I/O, it's certain CPUs like Intel 8080 and a few other legacy CPUs. They used to have certain pins on them. So if we represent here the CPU, actually Intel 8080 I think was a long chip like that. It had before, besides the regular pins for accessing memory, it has also other pins for accessing input-output devices. Like it was basically, let's say if you have here a keyboard, these pins would be connected and enable the keyboard, and this keyboard will provide back data. So it has two ways of actually getting data inside the CPU in other way, from memory and from input-output devices. And actually it had different instructions, the CPU inside. For accessing memory, usually it had those instructions with MOV, similar to what we saw yesterday in our virtual CPU. And for accessing input-output devices, it had in, I believe, and out. Different mnemonics that developers had to use if they wanted to access these pins and access these devices, or if they used MOV, the CPU would go directly into the memory and bring data. So that's why this this basically implementation of the CPU, it requires both access to memory and input-output. And actually in the implementation of this Altair 8800, the serial port is connected to this I/O port based on what I studied, and we need to make sure that we implement it correctly here. All right, so it's now time to put this one into the code. Let's see how we're gonna use the CPU from inside the code, and how we're gonna implement the memory and the other devices there. All right, so it's time to switch here to the code. Let's put this notebook on the side. So the CPU, first of all, this is the program. Maybe you should have also, yeah, we can leave it here. Let's have this one in, call it basic, and let's put it in an array. Alright, I hope that my editor produced a problem. I hope that this is okay. Just really quickly, let's print this one. Let's print, what is the length of this basic interpreter? Less than 2 kilobytes. A full basic interpreter implemented in less than 2 kilobytes. All right, so let's see how can we instantiate the CPU. Notice here that I placed the CPU in a different code page, and actually this is a feature of this CodeGuppy environment. Whatever you place in another code page, you can access it like a module, similar to Node.js environments. The only difference is that all the functions and all the classes are automatically exported, so you don't have to export them manually here. Therefore, in order to use it from here, all you have to do is basically, you can say const, and let's notice the class I8080, and we can import it here like this. I8080 equal require of CPU. All right, so we have access to the CPU, and now if we want to create an instance of it, we're gonna just say, let's say let CPU equal new I8080. So we create an instance of this one, but of course we'll have to provide a memory and an I/O. We'll have to provide a memory and an I/O. So the question is, we don't have these devices, so we have to implement them. So let's create another code page here called devices, and somehow here implement memory plus memory according to how we basically put it on paper according to how the author of this CPU envisioned that we have to do, as described here in this test. We have to create a memory, and then we have to create an I/O. So let's have a memory, and then we have an I/O. And the memory, it has to have basically a read, we said, a write. Let's implement the read method. Read from an address. It needs to have a write. So basically a write to an address and a number, which is an 8-bit number, basically, let's say an 8. And let's put also a load method on this one, because we want basically to load initially in the memory our tiny basic interpreter. So let's say data, we want to load data at a certain address. All right. I think just these two are requires. We'll have to see if it requires more. And then the I/O class, if we are referring back to how we said, it needs to have an input, output, and basically an interrupt, and we should be in good shape just to start it. Let's put also a constructor to this one. Constructor. All right. And now for the I/O class, we need basically to have an input method from a certain port. These are called ports when we are talking about input devices. They are not memory locations but ports. So we are inputting from a port, and then we are outputting to a port. It needs to have an output to a port and a certain number, an 8, let's say a number, an 8-bit number. And it said also to have an interrupt. But as far as I know, the machine that we are trying to emulate is not using interrupts in this way, so we'll just leave it empty. Let's make sure it has an interrupt. Even here it's empty, but anyway, we're gonna use it empty. We're gonna leave it empty. All right, so we have the two classes, the memory and I/O. So what we have to do right now, let's put a constructor to this one as well. We have to go in the code here, and similar to how basically we created the CPU, let's have also the memory. So const memory, comma I/O equal require devices. All right. So we require them. Now we can create an instance of them. So let's say let memory is basically new memory, yeah, or mem. We name it mem, new memory, and we have to load it right now. We can load it. We put a method on it called load. All right, we put a method called load, and let's load the basic interpreter at address 0. As far as I know, the address should be basically 0 in case of the Altair 8080, so the interpreter will be loaded at the first address where the CPU will start executing. And now let's have also the I/O is new I/O. All right, and then the CPU takes this one, and the CPU, if we are reading here, in order to execute an instruction, now we have the CPU prepared. I think we can call instruction on it and can execute an instruction. So what we're gonna do, we don't know how many instructions to execute, right? So we need to call instruction. So basically this will make the CPU tick, 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 and execute instruction by instruction. So what we can do, we can have a function loop, which is a special function in CodeGAPI. It's coming from the P5.js library, and this function gets invoked for us like 60 times per second by the browser. And what we can do here, we can have call that one CPU instruction in here. Yeah, it's called instruction. Yep, this one, which triggers execute next PC byte. Seems correct. You know what? Actually, you can do more. The CPUs are usually supposed to run many instructions per second, not only 60. So let's execute several CPU instructions inside the loop like that, just to make the clock tick faster. Actually, instead of doing that, let's put a small 4 here for let I equal perhaps I don't know, 1000 instructions. So 1000 times 60,000 instructions per second. It's still a slow CPU, but let's have it this way. All right. So we have the CPU, everything is wired. Let's run it now. Oh, we still have this number here we're printing, but nothing else happens. And of course, nothing else happens. Of course, nothing else happens. So the problem is that we have we have this tiny computer, and we need to wire to the computer a Teletype machine. Let me actually yeah, put them here to not move them easily. And we need to simulate somehow. This will be the biggest challenge right now. How do we simulate this machine? So first of all, we need to wire them. And I'm not an expert on this one. This computer was way before my time, and I couldn't find some very good information on internet related to what port this machine was connected, but based on some GitHub repository, actually let me see if I can find it, because we need to refer to it. So I think it was in the context of an Arduino project. Arduino Tiny Basic 8080. Let's see if this one. Yes, so in the context of analyzing the source code of several projects, not this one, let's see, I found out that basically the ports that were used inside this machine. So coming back here on our paper, what I discovered, and again, if you have better information, feel free to put it in the comments, is that inside here we have port 0 that basically is used for status. And then port 1 is basically used for input and output. So this is both output to printer, to this piece of paper that is here on the Teletype machine. It will start to print, and also it's used for input. So it's bidirectional here, and the status, if basically the port is available, it should be 22 in hexadecimal, and if it's not, should be 02. So we need right now to put this information in our program. There is another aspect that we need to do. We need to see how we simulate the printer here, this input. Do we type on the full screen? Do we accept input from the keyboard, from the PC keyboard, and send the keys back to this virtual CPU? Inside here, we have basically, inside this box, we have the Intel 8080 CPU. And we're gonna also add 4K of memory. And of course, we have that I/O port that is connected via the serial to the Teletype machine. All right, I put some thought about how to simulate actually this, or what kind of UI to implement to this one, and I'm thinking to implement a little bit more modern UI than it was used back in the day. So back in the day, you are typing on these Teletype machines, and the keys were appearing on the screen. So we just had an empty, or on the screen or on the paper. I'm thinking to simulate this one a little bit different. I'm gonna place on the canvas a text edit control in read-only mode, which will be basically the output. whatever the program will output, it will come here. And I'm thinking to place also a smaller text input, text edit control. This will be the input. And eventually when we are pressing enter, whatever we are typing in here, we are sending via the serial or via that I/O port to the CPU, and then hopefully the CPU will send via out something here. So basically here it's the I/O.output. We have to wire somehow this one and output in here, and this guy here we have to send it to I/O.input somehow whenever we press basically enter on the keyboard. And why I'm thinking to do it this way, normally on a Teletype machine, type letter by letter, this would go in a computer, will be analyzed, and eventually a feedback will be sent back. But this kind of method, it's a little bit difficult on modern computers, it's difficult to edit. So by having it in this way, we can write whatever we want. For instance, we can write here print, and if we make a mistake, you know, we can move the cursor back and forth. We can basically make sure we're writing correct statement, and then when we are pressing enter, we're gonna send this one, and hopefully should work this way, like this one. All right, so we need to create the UI, basically this. We wire up the CPU, we wire up the I/O. We didn't write the logic yet, but let's focus on creating the interface, because things will start putting motion once we create this one. So what we're gonna do, we're gonna use we're gonna use create edit, that it's available here on the platform, and create edit takes 2 parameters for the position, and then 2 for the size, and you can ignore the last one if you want a single line input. All right, so let's have it at the beginning here. Yeah, let's have it at the beginning, or somehow here after the basic one, right? So let's have a const txt output is create edit, and now we have to provide some the coordinates. Top left corner, let's say starts at 1010 and goes 770. Our canvas resolution is 800, so yeah, we can go 780, something like that, and 500. Let's have it, let's take a look. All right, this will be the output. Probably we can go 550 pixels down, 550 pixels down, and also what we can do, we can say txt output dot read only distro. And again, this is a very rapid application development type platform, but if you are doing this in HTML, you can obviously use a text area or some other element of that kind. So let's place a text input beneath this, below this one, const text input, create edit, and we also 10 on horizontal, and now should be probably, if this one goes to 550, 570, and the same size, 770. Let's see. All right. Looks correct. So here we want to print something to say list or some sort of basic command, and when we press enter, we want to send this one to the I/O of the CPU. So we're gonna have to implement probably some key pressed event. Let's implement it here. Yeah, let's implement it. Function key pressed, just to have it handy, and eventually say if we press key code equal enter. For now, we'll not do anything. Let me just say txt output dot text plus equal something, just to make sure that it's working. Enter. Yeah, we're in good shape. We wired them here. We'll have to see what we are doing. All right, so we have a UI that is basically by far not similar to how the user experience was on that machine at that time, but it's a little bit of a, you know, modern take on the Altair 8800. We have this UI, we have the CPU that we took from this GitHub repository. it's now time focus on these devices here. All right, so let's have basically the memory, and we said let's give it 4K of memory. Let's say this mem have an internal property, new array of 4K is 496, right? 4 times 124, 496. And when we are reading, basically we are returning this.mem from the address ADDR. We are returning that location, and when we are writing, we are doing the opposite. This.mem of ADDR equal N8. All right, so this is our memory, and we have to load it here. We have to load the data. So let's have a for let I equal 0. This is an array of data. Let's put an array of data. I less than ar data.length I plus plus. And what we have to do is to say this.mem of ADDR plus I, right? We are starting to fill from this address on equal to AR data of I. Yeah, in our case, since we are loading from address 0, it doesn't matter, but just to make it a little bit more generic. All right, so we have a very, very nice memory class. If we run it, obviously nothing happens. We don't expect to happen anything. But let me just share this program with you on the chat. And at one point, hopefully, the program will function. Hopefully. So this one is Altair 8800 Tiny Basic. All right. So from time to time, I'm going to save it, and you can reload it on your side, and hopefully will start working. So we are still on the devices section. And now the biggest challenge here is how to implement this one, this input-output device. We need to wire up like we put on the paper, and we said that the port 0 is the status. And again, if you have more correct data, please correct me, but based on what I found from this C++ or C repositories is that basically there is port 22 for start, there is the value 22 return on port 0 for OK if there is data, and then port 1 is used for communication. So I'm thinking here to do something else. The input output is connected. Let's have another device here, class TTI, which is the Teletype machine, right? And then we'll make the input output take a parameter just to link them more nicely. So the CPU is connected to the input output initially, right? So the CPU is connected to the input output, and the input output will connect it to a Teletype machine, which is basically our UI, those text boxes that we put the text box out and text box in. Let's have this one, the Teletype machine. So this one will be a constructor, and this one, let's have a txt input on the constructor and a txt output on the constructor. Just like this, right? And then let's wire them correctly now. We go back here, and the I/O, we're gonna make it take an argument. We'll have to take an argument, which is the Teletype machine, and we'll have to construct it first, that one. So let's construct Teletype is new TTI, which we have to import it from the same devices. And the Teletype will be connected to the txt input and txt output. Input and txt output. Let's see if we put the order correctly. Yes, first txt input, second txt output. The Teletype is connected to this one. The I/O is connected to the Teletype, and the CPU is connected to the I/O. Looks correct to me. And of course, we have the memory with the basic loaded, and this is connected also to the CPU. All right, so hopefully I connected them correctly. So let's go in the devices then. So we are moving in this way the entire responsibility of the input output. We are moving it into the Teletype device. So this one basically will have to provide the status and have a read and a write method that we're gonna write the input and the output. We're gonna wire them to that. So let's have here a function, a method get status, and also have read, and also have write. Right? So if we want to send something to the teletype, we'll say write. If we want to read something, we're gonna say read, and something like that. So on that serial, they are not. We are circulating ASCII codes, not the actual ASCII, but the actual ASCII code. So let's write here for a second. So we are sending a code. So what we are supposed to do, if we want, we have to take this one and put it in the txt output area. So we have to convert it. So in JavaScript we have string. It's called from char code, right? Something like that. And then we have to provide the code here, which is this one. Hopefully, our basic interpreter, when we'll run, we're gonna write into this one and provide the code. And let's say txt output dot text plus equal chr. So that's the idea how the teletype or the class will interact with this one. Now we should implement the read, and the read we basically should read from. We can read from. We are not reading from the txt input. Let's do it differently. We said that only when we press we are reading. So let's make when we are pressing that text that was written in the txt input, let's put it in a buffer, some sort of a buffer, right? So first of all, yes, let's do the buffer, but also this one that were sent on the constructor, let's set them in some internal properties, because we're gonna need them. Equal txt input, and this one is txt output, and of course here this one should be this dot. And let's have this teletype also have this this buffer, basically like an array. So when we are pressing enter, we're gonna set this buffer, right? So here when we are pressing enter, we want to somehow set that buffer property there. So here we should take the message somehow, the text. Yes, when we are pressing enter, we do have access to the teletype from here. So we should say teletype dot, let's say dot input message. We are inputting into the teletype the txt input dot text, and we are pressing also on enter. Let's press also on enter, because we're sending that with an enter after that. And let's clear up the original text so we can type more. Equal like that. We are writing it. So let's write this method. We can write a method on the teletype called input message that will take a text, basically nothing else than a text, and this one should set up the buffer, or can set up the buffer, or we can just copy it in another one. But I'm thinking, yeah, let's have the buffer like a binary, like an array here, right? So anyway, we're gonna see what code we are writing here. I just want to test the code for now, see if this once works. So if we are pressing enter, right? So if we are typing here something, we are pressing enter, it disappears, probably goes inside this method, and this one we are not doing anything of it. So we have now to put the codes in this buffer, yes, and I want to have it like an array and not as a string, because anyway on the serial connection between the CPU and the teletype we'll have only codes. So I can just convert it to codes from the beginning here. So let's say for let chr of txt. In JavaScript we need to have access to a code from the chr, which is basically chr code add, checkcode add. Checkcode add. I think checkcode at 0 because we have only one. Yep. So that one should return the code. Now this one, of course, these are Unicode functions, but we're gonna make use sure we're gonna type just ASCII characters in the text input, and then the code will gonna match the ASCII code, which is basically this very old machine was using. So let's push into the buffer, this dot buffer dot push the code, right? Just like that. We are inputting, and just to make sure that this one arrives there, I want to do a small test. I'm gonna just push this dot buffer dot length, just like this, plus \r. It's a temporary test. Okay, 311. Okay. Oh, so we get the. Okay, so they get accumulated in the buffer, which is good. Which is good. We want to accumulate them in the buffer. We don't want to remove the old buffer because the buffer is supposed to be removed when we are reading it from it, right? So when the machine is reading it, it's basically it's supposed to remove the buffer, right? Right. I hope so. So and then if we have this one prepared, if we have the write is writing there. Now the buffer, when we are reading, we should read it from the buffer, right? So we should return when we are reading this dot buffer. Let's implement, actually not let's implement, we need to implement it like a FIFO, because the first character that enters needs to be the first character that outputs. So we're gonna use shift here, not pop. But we'll put a condition, return this dot buffer dot length is greater than 0. If yes, we'll shift. If not, we're gonna send a 0, which is basically the null character. Just hopefully this will work. Right? And now we have to write the status here. And this one is the one that I don't have too much information about it. But as far as I read from this GitHub repository, is basically if we have data, we can send a 22 character. If we don't have data, we need to send a 2. Okay, so you know what? We can actually use the same construct here. If we have the data in the buffer, send a 22 index decimal. If not, send a 2. All right, so that should give the status. Now, this is the Teletype machine we implemented it. So basically, it's connected to the input-output, basically to the UI. This method, it's an internal method. It's used to fill the buffer when we press enter. Then get status, it's something that our I/O interface should call. And if basically this is 022, we're expecting this read to be called. And then write is wired up to the txt output. All right, looks correct until this point. Let me run again the program. Okay, I don't have any error. Any error? Because I don't have an error doesn't mean things are right, but at least it's better than hunting errors. So right now let's code this class, and we said also, as we put here on the paper, that let me review here really quickly. Yep. We have right now to focus on, we're gonna check if we are reading for port 0, we have to ask the machine for get status, right? We already implemented that get status in the TTI. So, and that one is returning these numbers already. So when we're gonna implement IO, we're gonna say, okay, if it's an IO request on port 0, then if yes, then ask the TTI to provide the status. If it's an IO request, an in request on port 1, we're gonna ask TTI.read. If it's an IO write request on port 1, we're gonna say TTI.write. And of course, this one we are asking TTI.getStatus. Get status, like this. And as you saw, write we implemented, basically we are going to the txt output. So whatever it's sent on port 1, it gets into the TTI class and then gets to TTI out, and the read sets that buffer, which is coming from TXT input. So since that these ones are wired up, so finally it will reach the UI here, coming from ports via the IO via these classes, and it reaches there. And we also implemented the memory as the 4K. We implemented basically for the memory exactly to that specification. We implemented the read and write. All right, so what we have to do is now implement this IO and check for if it's port 0, and if it's port 1, do this kind of things. All right, so this is next. I'm gonna keep this one handy if in case I'm gonna need to refer to them, but that's our intent. So we are here on the IO class. Let's save really quickly an internal instance to this TTI. And now on the input port, we can do an if, or we can do a switch. Let's do a switch. If we are requesting to get a read from port 0, let's say case 0. Let's write it in hexadecimal, like cool kids when working with low-level stuff. And now this one should just return 0 is the status, right? So let's say here status. Return this.tti.getStatus. I think yes. Get status. Again, this one is returning 22 if we have data and 02 if we don't have data. Hopefully should be okay. And now if we are reading, let's have another one, case 0x01. If we are using this one, this is basically for input. So this is serial input. So let's wire this up to this tti.read, right? We already wrote the function here, and we have it, which should take it from the buffer. So as you can see, we are not emptying the buffer. The program as is running, that tiny basic as is running, will make IO requests, will hit here read, and read will trigger our own read, which will cause the buffer to shift. So basically the buffer will get less and less there. And maybe other cases here, we can put a default. I'm not sure, actually for sure, the Altair 88 machine used other ports, but I think in the simplest form we can just live with these two ports, 0 and 1. Other ports were connected to other devices in more complex configurations. So anyway, I don't know what to do here. We'll just return a 0, but this hopefully will not reach this one, because that's not very good. And now for output, we should do the same, right? We should switch also, we should have a port, but in case of output, I think we are just handling the port 1. And we can have a default as well, but not return. In case of port 1, we're gonna wire it up to this tti.write, and then we are writing it this N8. Let's check the write here, if it accepts. Just a code, correct. Just a code. So this is a number on 8 bits. It's a code basically that will be converted to an ASCII when we are writing it. And we are breaking here. And here we'll just break. We don't know what code to put here. And as I mentioned, we don't have to handle interrupts for these cases here, so we leave this empty. All right, let's run it and see if it boots up. Notice here, tiny basic. Okay, we got prompted with a prompt. We didn't wrote this one. So what's happening, that program boot up and actually wrote. So our program works. So let's write something here, list, enter. All right, it accepts input and produces an output. So let's type a small program, 10. Actually, let's put, this is a conversational kind of language basic. So we can put simple instructions. So let's say, hello, basic, enter. And we see the output. Hello basic. Let's calculate something. Print 2 divided by 3. 0. Huh. Print. You know what? Maybe it doesn't have floating point mathematics, this one. Let's divide 4 divided by 2, and it's 2. All right. Let's use 1 plus 3 plus 2 times 3, and it's 7, which is working correctly. Print 10 times 2 minus 5, 15. All right. List, we don't have any program. Now, in BASIC, to input programs, you actually have to input them with line numbers like this. So let me input a quick program. If I still remember the syntax of BASIC, for I equal 1 to 10, 20, print I, 30, next I, issue a list, and we see the listing, and issue a run. Now to run the program that it's in memory, and we see the numbers from 1 to 10. List. Well, this is fun. Let's if we want to change line 20 here, we have to overwrite it, writing again 10. Or since we implemented this one, this is one of the reasons we implemented this one in this way. We can interact, you know, we can edit this much nicer than on a terminal style computer. Let's time multiplication table with 5. If we'll run it, all right, we see the numbers. So this is fun. Now, what you can do as a next step, you can go ahead and find perhaps a book of old BASIC programs that are compatible with Tiny Basic, and there are books published on this subject. You can find books and maybe type in a small game here. Let me run here again. Something 10 input A 12 20 print hello A. Let's see if input is working. Yes, A equal Marian hello. I forgot the syntax. Oh, I think when we are working with string, it's you have to put a $sign in BASIC, something like that. I don't recall. Let's run it. It's not a $sign. Maybe $A. All right. I forgot the syntax of BASIC, but as I was mentioning, you can go ahead and find some historical BASIC programs that you can run them on Tiny Basic. Also, what you can do, you can basically, and let me place this BASIC interpreter in a separate page here. Let me name it programs, just like that. And I'll remove it all together from here. So this one is function get basic, get tiny basic. And I can just return it. This is Altair tiny. This is Tiny Basic basically. But if you look deep enough, you can also find probably the Microsoft Basic. So you can go ahead and put it there in the programs here, and you know, you can have tons of fun with these ones. Const, let me have it, programs equal require programs, and now let's see, instead of passing basic, we are passing programs dot get tiny basic. I think this is the name. Right. So if you put there the Microsoft Basic, you can also run that one. It still runs. Also, you can find books with Tiny Basic programs, or perhaps Microsoft Basic programs, and run them on this machine. It's very impressive what can be done in 4K of RAM, and actually the interpreter is in 2K of RAM. You have about 2K left for your tiny programs here. And if you are willing to research a little bit more, like we implemented here the devices, the IO class, and actually just the IO class, the memory can stay the same, you can handle other serial port requests, and you can make it answer to requests for disk drives, which are not that difficult to implement. And at that moment, you can even run CPM, which is basically a full-blown operating system on top of this kind of emulator. And once you are running CPM comes with its own programs that you can run and execute, and you can have tons of fun. Another idea, you can integrate this interpreter in your web page. Perhaps you can change the interface a little bit. You don't have to have it like this. What you can do, you can eliminate the input area here, and you can have a method init, and on that method init you just feed via serial a full tiny basic program, and then you trigger it with a run command, and that one will produce some sort of calculation or effect that you can capture it back. Lots of possibilities here. If you build something interested with this one, feel free to leave it in the comments. Again, this was about creating an emulator, a very emulator, beginner style for this machine, Altair 88 computer. I used lots of references that I'm gonna link into the description, both for historical references, also for documentation and some GitHub projects to discover the details about this machine. But I think it was an interesting project to be done in JavaScript. Of course, the credits for that CPU emulator and a lot of information for serial devices goes to the authors of those repositories. All right, so with this being said, I want to wish you happy coding. Thank you for watching, and see you next time.